Hey team, today I'm going to show you how to use what's in one of these and a few extra components to drive one of these to make some really cool lighting effects for your Halloween haunts like this. Somewhere.
Dead men tell no tales.
Now, because there's not much information around on these parts, we're going to do some kind of analysis of our own to find out how these things are working and what they're doing. We're also going to get into a bit of transistor theory, which will help some of you kind of tweak the design for the components you've got available, maybe a different light output, maybe a different transistor. But if you want to take my word for it and just copy the build as I've done it, skip on ahead to here, and then you can just build it as I've shown you. So first thing we need to do is to crack open our tea light and see what's inside. So we have got a CR2032 lithium battery. That's a 3-volt supply, so we know the thing can handle 3 volts at least. And it looks like the best way to get into here is actually going to be okay. So we literally have got a LED and some sort of really cheap built-in switch. So it is literally just the one component connected to the one battery. So we don't know much about these, so I think what we'll do is we'll connect up to the power supply, we'll run it through some voltages and see if we can work out what it's doing. Okay, so hopefully you've got some picture-in-picture action going on here. I'm just going to turn on the power supply. So I've got it set to 2 volts and limited to 1 amp. Hopefully we won't get anywhere near that. Let's just turn on the output at 2 volts and see what that does. Okay, it's working. Might be a bit washed out in the camera, so I want to stick a dead rat over there, see if that helps it. So, yeah, not so much. I want to dim the lights a bit. But take my word for it, it's flickering away there nicely, as you'd expect. And I'm getting no current reading on my power supply. And I suspect it's a cheap pot power supply, so that ammeter's not reacting fast enough. So I'm going to put my proper ammeter in line as well, and we'll see if it sees what current it's drawing. So we've got the ammeter connected here, and what we're going to do now is we're going to step through the different voltages up to 3 volts, and we're just interested in what's the maximum current being drawn, because the LED is obviously flicking on and off. When it's on, it's going to be drawing more current when it's off, and we're really interested in that kind of peak current. So we're just going to step through 2 volts, 2.2 volts, right the way up, 0.2 intervals, up to 3 volts, and just generate a little graph of kind of our voltage to current draw ratio. Right, so just for completeness, I've wired up the LED to the 12 volt power supply in line with a 2700 ohm resistor, which should limit the current to around 4 or 5 milliamp. And we'll just have a little look what's going on. So as you can see, it's going up and down, it's on and off. And so we're measuring that across the resistor at this point. So if we look at the 2 probes, we can see when it's on, we're getting a 9.8 volt drop across that resistor. And when it's off, we're getting a 1.3 volt drop. Now that 1.3 is quite crucial because it means when it's fully off, it probably won't be low enough to turn off the transistor. But we'll come back to that in a minute. So before we go any further, let's get into a bit of transistor theory. So I've said I wanted to use the 2N3904 primarily because I had quite a few of these in stock, but I'll go through kind of why. Now, if you want kind of detailed, educational tutorials on transistor theory, there's lots of other ones out there. So I'm going to run through the bare minimum we kind of need to get through this. So up here you can see we've got a symbol for our transistor, and basically if we put a voltage across the base and the emitter, so it's between pins 2 and 1 there, then a voltage will start to flow between 3 and 1. And these are current-based devices, so depending on how much current we can force across that junction, depends how much current will flow through this junction. So there's a couple of kind of key things you want to look at here. So first one, the collector emitter voltage. This is the maximum voltage we can put across junction 3 and 1. So that's currently 40. So our plan is to use a 12 volt power LED as our output, so well within parameters there. Emitter base voltage, the maximum 6 volts, don't worry too much about this one. Right, next one, collector current continuous. So this is the maximum current, continuous current again, we can put across these junctions 3 to 1 here. So 200 milliamps constant current, well below, I think, the estimated 70 milliamps needed for that power LED. So we're well within the thresholds. So, but if you're kind of picking your own device, those are the figures you might want to miss. Collector emitter voltage, how much voltage can I put across there, and how much current can I put through there. So the next lot of information we're primarily interested in are these on characteristics. Now, because we're going to use our transistor as a switch, we are working in a region called saturation mode, and the saturation mode basically means we're either fully on, saturated, or we're fully off. Some of the other kind of transistor related videos, you'll hear people talking about the beta value, and beta is a kind of a current gain ratio. So if we have a beta value of 10 and we put 1 milliamp into the base, we'll get 1 times 10 milliamps through the collector emitter junction. Now, very rarely will you see beta quoted in any of these figures. The equivalent of beta is this H, capital F, capital E, which is our DC gain values. Now, if we look down this table here, you can see for the 3904, there are lots of different values coming up at different collector currents. Now, when we're designing, because we're designing it as a switch, let's use the worst case scenario for our device. So looking at the 3904, the lowest gain we'll get is 30. So if we design for an HFE or a beta of 30, we know we're always going to kind of we're going to be saturated when we use the right base current with those figures. Now, there's a couple of other numbers down here as well. So the transistor is not a perfect device. So when we've got it fully turned on, there's a voltage drop between the base and the emitter of minimum 0.65, maximum 0.95, and again you'll see in other tutorials they talk about a VBE SAT of 0.7, which is a good kind of rule of thumb design figure. If you want to be more thorough, go with the worst case scenario, which is there's a 0.95 volt drop across that junction when it's on. Same here, the collector emitter junction, it's not perfect. Even when we're in full saturation, we've still got a 0.2 or a 0.3 drop across that collector emitter junction, which we can factor into our calculations if you want, but they're fairly trivial from our perspective. So I probably won't bother using these. However, I will be using these. Right, so I think we've got everything we need to know now to go ahead and design the circuit. We have got, what do we know? So we know our 2N3904 has a DC gain, or beta, or HFE, of 30 as a worst case. We also know that the base emitter voltage drop is about 0.95 volts when it's fully saturated. We know that in order to turn the transistor off again, we've got to pull VBE down below 0.65 of a volt to cut it off. So off camera, I did some tests with the power LED, and at 12 volts, that draws about 70 milliamps. And we've also got our graph down there of our kind of LED voltage current relationship. So where do we start? Okay, so first we need to calculate the base current needed to saturate the transistor for our power LED. So we know the power LED again draws about 70 milliamps. We know the gain of the transistor is 30. So in order to work out the kind of minimum base current we need, it's simply the output current 70 divided by the gain 30. So that's 2.3 milliamps. Now that's a minimum. So we want to go above that to make sure it's fully driven on, but kind of not massively above it. So let's have a quick look at the graph we created, and let's pick a nice round value of above 2.3 milliamps. So let's just kind of arbitrarily pick 4 for no reason other than it kind of falls nicely on the 2.2 volt drop needed to that current. So we need to make sure we've got a 2.2 volt drop across the LED, and if we do, we know we can have about 4 milliamps coming through it. So next we need to calculate the current limiting resistor for the flicker LED. Now in the drawing you can see we've got R1, R2, and that's a voltage divider, but for the sake of calculation, let's just consider we're connecting that LED straight between 12 volts and 0 volts, so we need a current limiting resistor to stop it frying. So using Ohm's law, we know the power, the voltage from the power supply is 12 volts. We know we want a 2.2 volt drop across the LED to give us the 4 milliamps for the base current. We also know when it's fully saturated, there's about a 0.95 volt drop across that base emitter junction. So we need to basically drop the rest of that voltage across that resistor. So that remaining 8.85 volts, we've got to drop across the resistor. So just using straightforward Ohm's law, 8.85 volts divided by the 4 milliamp current we want, so it gives us about 2,212.5 ohms, 2K2 nearest values. So the total combination for R1 and R2 is around 2,200 ohms. So let's now calculate the individual values for R1 and R2. So we've got the voltage divider kind of here. We know R1 plus R2, so the total resistance we need to protect the LED, flicker LED, is 2,200 ohms. But we also know that when from the oscilloscope view, we also know that when the flicker LED is in its off phase, there's still about 1.3 volt residual voltage across that resistor. Now, as we said kind of before, we need to pull that base voltage down below 0.65 volts in order to turn the transistor off. So 1.3 volts if we just had that straight across the top of that one, it's not going to turn that off. So we have to create this voltage divider. Now, standard kind of formula for voltage divider is V out equals V in times R2 over R1 plus R2. So we want V out to be less than 0.65 volts to turn off. So let's pick around 0.5 volt just to kind of be safe. And that's 0.5 volt when the flicker LED is off. So we've still got 1.3 volts available across those resistors. So rearranging the formula to find R2, V out divided by V in times R1 plus R2. Now, we're trying to find R2, but we've got R2 in our equation, so that makes it tricky. However, we know the total value of R1 plus R2 is 2,200 ohms. So again, it's kind of straightforward calculation. So we've got the half a volt, which is the voltage out we want to get to, divided by the voltage in, which is the 1.3 volt, which is the voltage, residual voltage when the flicker LED is off. It still stays at 1.3 volts. Times by our resistors, our total resistance, that gives us 851 ohms. So I think our nearest 820 is the nearest E12 series value for that. Now we know R2, and we know R total is just R1 plus R2. We can just do a straightforward subtraction to find out the value of R1. So 2,212 minus our preferred value, 820 ohms, that leaves us 1392. So I think our nearest value, again, E12 series, is 1,500. So we end up with an R1 of 1,500 ohms and an R2 of 820 ohms. So when the LED is off, our V in is down to 1.3 volts, so that we should have about 0.5 volts across the V out. 0.5 volts should be enough to pull that transistor down into its off state. So let's go and pop it into the breadboard and see if it works. Now, got all our components together. Got our Eagle Eye LED. That's connected up to these two probes here, just to make it easier to stick into the board. Got a power, transistor, two resistors, and our flicker LED. So let's get going. Yes, let's stick the emitter down the bottom. Okay, so we've got the 120, and this one must be the 1K, 1K5. Right. So 1K5 goes from the base through the LED to 12 volts. And then we've got the 820 ohm, which goes from the base down to the 0 volt rail. And we need to jump the emitter, ground rail as well. Positive of the Eagle Eye LED, positive there, and the negative of the Eagle Eye to the collector of that transistor. Okay, so we've got the power. There, so we can see it. Right, let's turn on the juice and see if it releases the magic smoke or works as planned. Oh yeah, so hopefully you can see that flicking away nice and bright, nice and powerful. It's also doing its thing. There there, it works. You can see from the power supply as well, we're kind of seeing kind of spikes between 20 and 50 milliamps, so I suspect we're in the right ballpark for the 70 for that. All good in the hood. Because there's only 4 components, a jumper wire and an external LED, they're quite easy to knock up one of these on a little piece of scrap Vero board you've got to line around. And again, you could stack multiple of these on a single board if you like as well. So single power supply, 3 outputs. Ideal for a home horn or some other small lighting display. So hopefully you managed to follow along with that build, and some of you who watched the kind of transistor theory and the extended piece in the middle, hopefully there's enough kind of information there now if you need to go away and tweak it and make it your own. And happy Halloween or whatever display you're using it for. Thanks for watching. Goodbye.